A metering pump does not begin by measuring liquid electronically. It begins by moving a precisely defined cylindrical surface through a controlled stroke. Every change in working diameter, surface condition, seal contact, or axial alignment changes how that physical volume is created. The polished ceramic body shown here is therefore part of the measuring mechanism itself. When the high-pressure seal remains stationary and the smooth cylindrical member moves through it, the more precise engineering term is plunger. Some pump designs and commercial descriptions still use piston for similar reciprocating parts, so the final name depends on the seal position and the chamber architecture. In either form, the working surface must repeat the same path without damaging the seal. The first material demand comes from repeated sliding contact. Dense 3 Y-TZP SB zirconia is commonly referenced around 1200 to 1350 Vickers hardness. That hardness helps resist abrasive scoring and gradual diameter change when the surface moves against seals, sleeves, or pump liners. Wear still depends on particles, contact pressure, lubrication, alignment, and the counterface material. A long plunger also has to tolerate handling, assembly stress, start-stop loading, and occasional side contact. Yttrium-stabilized zirconia gains unusual toughness through stress-assisted phase transformation near a crack tip. Representative values for this material family are roughly 900 to 1200 megapascals in flexural strength and 6 to 10 megapascal root meters in fracture toughness. Finished part strength remains geometry dependent. For a plunger, surface finish is not cosmetic. It influences friction, seal wear, leakage pads, and particle retention along the stroke. The series shown is specified with a polished working surface down to an R value of 0.02 micrometers. That figure must be verified on the functional diameter, because scratches, waviness, runout, and edge damage can matter even when the average roughness value is low. The basic metering relationship is geometric. Ideal displacement per stroke equals the plunger cross-sectional area multiplied by stroke length. For a circular plunger, that is pi times diameter squared, divided by 4, then multiplied by the stroke. The square on diameter is important. A small diameter deviation changes displacement more strongly than the same proportional change in stroke. The seal does more than close a gap. It separates the pressurized fluid chamber from the drive side while allowing reciprocating motion. Contact pressure must be sufficient for sealing without creating excessive friction or heat. The ceramic diameter, surface finish, seal material, contact length, fluid chemistry, and pressure cycle all influence whether the interface remains stable across repeated strokes. A polished surface can still fail early if the plunger enters the seal-off axis. Misalignment concentrates contact on one side, raising friction, seal deformation, and bending stress at the ceramic to metal transition. Straightness, roundness, concentricity, connector runout, and guide support therefore belong to the same metering problem. Across metering and dosing pumps, there is no single cross-industry plunger diameter or length that can be treated as universal. Each pump head establishes its own seal diameter, stroke, chamber volume, guide spacing, and connection method. A replacement dimension may be standard within one pump platform, but outside that platform the same value has no independent meaning. A complete drawing should separate the working diameter from the mounting geometry. It should define overall length, seal contact length, stroke zone, end radius or chamfer, shoulder position, metal connection, joining method, and the required relationships among straightness, roundness, and concentricity. Hybrid ceramic metal assemblies also need a controlled load path so the connection does not introduce local bending into the ceramic body. In a precision chemical dosing pump, the plunger retreats to draw fluid into a defined chamber and advances to discharge that volume. Diameter and stroke establish the geometric basis of each cycle, while valves and the fluid system determine how closely delivered volume follows the ideal displacement. The polished zirconia surface repeatedly passes through the stationary seal as chamber pressure rises and falls. A stable diameter and controlled finish help limit scoring, friction, and seal damage, but alignment and seal selection remain decisive. The ceramic cannot compensate for a distorted housing, contaminated fluid, or an unsuitable sealing material. Dense zirconia is considered when the working fluid can abrade or chemically attack the moving surface, or when metal contamination is undesirable. Compatibility still depends on concentration, temperature, particles, cleaning chemistry, and exposure time. Precisely measured flow begins as a physical volume, 1 diameter, 1 stroke, and 1 polished ceramic interface repeating the same path.